Hello, everybody. Enjoying VCF East? That's right. Okay. So I have to admit, I didn't even know who this guy was until I pushed a door into him out in the hall. But then I found out he created UNIX. What can I do? Hey, everybody, he does not need an introduction. Please welcome none other than Brian Kernighan.
Okay, we will see if this goes and if we get another one of these feedback loops or something like that. Anyway, it's a real pleasure to be here. I feel like I'm definitely among my people. This is just incredible. Yeah, I was last here 6 years ago, in fact, almost exactly when Ken Thompson and I did a fireside chat in this very same stage. And that was an enormous amount of fun. And then, of course, events interfered like COVID and so on. So it's a real pleasure to be back. I'm very grateful to Jeff and Bob and Mike for putting together various things. This nice badge, it's Mike's work. So anyway, I'm going to make this as informal as I can. This was supposed to be another Q&A with Stephen Edwards from Columbia, but he is unfortunately unwell, and so I am going to talk at you for a little bit, and then we'll take questions until people run out, or I do, and we'll see what happens. Okay? But anyway, it's supposed to be fun, and I hope it will work for everybody. So I don't have to tell everybody here that Unix is important. No, I did not invent Unix. That was Ken Thompson and Dennis Ritchie, please. But it's obviously an important thing. It runs essentially everything that we use these days. Certainly it runs the internet in its original, not in its original form anymore at this point, mostly things related to Linux. So it's obviously very important for our lives in all kinds of ways. And of course, the lives of lots and lots of other people who haven't a clue what this is about. So anyway, Unix as an operating system was created, at this point I would guess, say 55 years ago or something like that. And it was created at Bell Labs in New Jersey. And for those of you who aren't from New Jersey, which is I'm guessing not very many, it was at Murray Hill, which is there. You can see it sort of to the west of New York. And in case you don't know where you are right now, you're down there in the lower right corner. So I'm going to talk about Unix. I'm going to talk about how it came to be, sort of those early days, and so on. And I'm doing it obviously not as one of the creators, but as a camp follower who happened to be in the right camp at the right time. Talk a bit about maybe what we could learn about software development from this, although I don't know how much of that is reproducible today. And maybe a bit about how to manage the creative process so that there's a chance for other things that work out as well that might happen in the future. Okay, so a bit of history first. In 1885, a long time ago, AT&T was formed. It basically coalesced, kind of bought up in the modern sense of taking little companies, bought up a bunch of telephone companies into a single product or service, and it provided telephone service for an awful lot of the United States for, at that point, close to 100 years. As time went on, they realized that they actually needed a lot more scientific expertise, that they couldn't just do things by cut and try. And so in 1925, they created an institution which they called Bell Telephone Laboratories. And the original version of that was in New York, roughly, was on West Street, roughly under the W in New York at that point. And so that was in 1925. And then during the war, they started to actually do things in New Jersey in particular. And then in the very early 1960s, they moved the operation from West Street out into suburban New Jersey. And I have a picture here. This is what it looked like in 1961, a nice aerial shot. And it looked pretty much like that for quite a long time, although things happened. But you can get a sense of the scale and so on from just the size of the building in comparison to the number of cars and their sizes in the parking lot. So I would guess that there were something like, and I was discussing this with somebody earlier just before we came in, about how many people are actually in that building. My number is sort of 3,000, but I would be happy to stand corrected by anybody who actually knew the answer. No problem. But in any case, call it 3,000 people, an awful lot of them with PhDs, doing fundamental research in a wide variety of topics. And they created at least a few things that you've probably heard of, like the transistor and the laser and fiber optics and things like that, minor things. Depending on how you slice it, something of the order of 8, 10, 12 Nobel Prizes. The nice thing about Nobel Prize winners is they can be sliced arbitrarily thin. And so any place where a Nobel Prize winner walked through the door, well, we have a Nobel Prize winner in our... So take that one with a grain of salt. So anyway, this was the research part of Bell Labs. And then there was, I don't know, call it 25,000 or so other people, not here at Murray Hill, but scattered around, mostly in New Jersey, but other parts of it, who were doing development work, trying to take the ideas from research and in some way or other convert them into useful telephone products and services. And of course, going the other direction, we have a problem in providing services and products. What can research do to help us? So those, as I say, were parts of Bell Labs, but not research per se. At its peak, I don't know what that would be, but call it in the 80s or something, AT&T was the nation's largest employer outside of the government with well over 1 million people. And you can see from that Bell Labs was a fairly small part of that. Okay? So most of the research that went on here was what I would call hard sciences, physics, chemistry, materials, things like that. But there was also a fair amount of work on communications, because this was a communications company. It was providing telephone service to the country. And there were a couple of people who showed up in that as kind of, I think, important contributors. Here's two of them. One is Claude Shannon, who basically showed that you could, in fact, transmit information over a communication system with arbitrarily high accuracy if you converted it into some kind of digital form and then encoded it in a reasonable way. He wrote this famous paper in 1948 called A Mathematical Theory of Communications that is sort of still extremely influential. So he was at Bell Labs for a while. He left in 1956 and went off to MIT. The other guy, Dick Hamming, is the guy who created error correcting codes. And of course, a lot of things work because, although something happens, you can actually use redundancy to figure out that something did go wrong, and perhaps with enough redundancy, even figure out how to fix it. So Hamming was at the labs. He's more or less the same era as Shannon, although he died a little earlier. But he was at the labs from 1946, just after the Manhattan Project, until 1976. And by an enormous bit of good luck, my first summer internship in 1967 was in the office next door to Dick Hamming. and so many of you have had this experience of you see me and you think, oh, I'm just going to bow before him. Well, no, don't do that. But I had that experience with Hamming. It's like, oh my God, this guy's important. And he's in the next office. And he turned out to be, of course, a super nice guy. And I knew him very well until he left to go to Naval Postgraduate School in Monterey. Anyway, after that, I moved from the 1967 era to the 1968 through 2000, where I was in the same office for 32 years. An island of stability in a sea of change, or something like that. And I was, it's true, and I was part of a group called the Computing Science Research Center, which was, at the time it was started, it was about 25 people who had been spun off from the mathematics research department. And their job was fundamentally to do stuff in this brand new area of computing. And so they worked on various kinds of software, including operating systems, languages, and so on. And it was mostly located in that top floor of what is called Building 2, roughly where that dot is, and the corridor between the two dots. So what were they working on? Well, one of the things that they were working on was operating systems, it turns out. And in 1961, we're going, ancient times here, MIT created a time-sharing system. The idea that there was a central computer and people could connect to it from various, in this case, remote terminals, teletype-like devices. They did that in 1961, CTSS, the compatible time-sharing system, and it was a roaring success. It really was a very, very effective system. I used it for a while. And so in 1965, they decided that they would do another system that would solve all of the drawbacks and deficiencies of CTSS, and of course create lots and lots of new features and so on. And it was going to be called an information utility, which if you think about it today, it's like cloud computing, but before there was a cloud. It was something that would provide centralized computing services for all kinds of people. And this was called Multics. And Multics, of course, turned out to be too slow, too late, and ultimately not enough, although people who worked on Multics will tell you it was a success. Depends on how you define it, I guess. But it had a lot of good ideas. Unfortunately, it was too late, too slow, and so on for Bell Labs, and in 1969, Bell Labs pulled out. They stopped supporting it. It had originally been a joint project of MIT, General Electric, and Bell Labs. You don't have to be much of a student of institutions to realize that something that involves a university, a company that makes locomotives, and a commercial research lab wasn't going to work too well, especially when they were spread across the whole country. Anyway, 1969, AT&T, I have a slide here, by the way. I should have showed this. CTSS was the work of this guy in the top, Fernando Corbato, or Corby to everyone. Just a wonderful guy in addition to being extremely smart. And then when Bell Labs pulled out of the Multics project in 1969, it left several of these people bereft. They had, they wanted to work on software. They'd gotten a taste for interesting computing environment, but they couldn't do it because they didn't have anything. And so they started to think about what to do. As that was going on, Ken Thompson was experimenting fundamentally with file systems, and he was using this machine, PDP-7. And PDP-7, there's enough experts here that if I say something wrong, correct me. But I mean, I'm older than most of you, but I don't remember as much. Anyway, this machine, I think, came out first in roughly 1964, and so it was totally obsolete by 1969. It was not a very powerful machine, and the phrase that goes with it is usually little used. And so Ken found this little used PDP-7 and realized that he could use it for experiments. At some point, he made this famous remark. He said, "At some point, I realized I was 3 weeks from an operating system." And I heard that somewhere. I don't remember where I heard it, but I decided, what the heck, I got to find out what's going on here. And so I sent mail to Ken, in fact, the obvious thing. And I got a response from him. At that point, he and I had both left Bell Labs. I was at Princeton, and he was at this startup. And this is what he said, that it was a file system implementation. He wants to test throughput, but he couldn't get data into it. It was too much work. And so what he did was to say, I could do something. So Bonnie and Corey, their son, went off to visit Ken's parents in California, and he said, I could do it. I just need these handful of things, a shell, an editor, and an assembler. And, 1 week each, it's all done. I think this sets a record for software productivity, which has never been equaled. Anyway, I believe it. So anyway, the PDP-7 then was a sort of proto-UNIX, and it clearly was useful, but at the same time quite limited because the machine was quite small. It had 4K of 18-bit words, so it really was small. And so a number of things went on in parallel, but fundamentally Ken and Dennis, Doug McElroy, and others lobbied Bell Labs management saying, please buy us another computer so we can do this. And what they wanted was a PDP-10, which at the time was $500,000. So it was a big 36-bit machine. And Bell Labs management, normally quite good, in this particular case, they'd been bitten, and they sure as heck weren't going to be bitten again. And so they kept stalling. And eventually, the folks were able to get the brand new at the time PDP 1120, which came out in, I think, again, 1970 or something like that. So they got, and it only cost $50,000, so a tenth of what they had been asking for. But it turns out, in fact, a fine machine to do UNIX on. And they promised, that is Ken, Dennis, and others promised to actually build software for the patent department so that the patent department could file patent applications in the proper form expeditiously, and that was successful enough that they were able to get real money. So there's a classic picture of Ken and Dennis standing, Ken seated in front of, I don't have to tell anybody here what those devices are. Everybody will recognize, Model 33 teletypes, deck tapes, all of that kind of stuff. This picture probably dates from 1971, but I'm not absolutely sure. But that's the machine on which the first real version of Unix was developed. And so the first edition, which was recognizably Unix, in use by a number of people, not a huge number, but a number of people, totally self-supporting. All the software that ran on it was developed on it. Recognizably, you would call it Unix if you stumbled into it today. And it supported things that at the time were kind of unusual in a lot of settings, like multiple independent and simultaneous users. So it was a time-sharing system in that sense. And oddly, it was actually well documented. In spite of being very much a research project, it was very well documented. And so, for example, here's the man page for the cat command from the first edition. And that's back at a time when man pages were a page, okay? Some things have not totally improved in the past. The other thing that's interesting about it, you notice down near the bottom a section called bugs. And this was actually a sort of an article of faith in the group that they would, if there were known bugs or mal features of some sort or another, they would show up in the documentation and maybe get fixed at some point or other. And that kind of, I'm not sure that still works or not. Anyway, that was the first edition in late 1971. New editions came along fairly regularly at that point, every 6 or 8 months, I guess. And so here's a market forecast for the second edition, which I guess you could argue in retrospect is a bit conservative, but anyway. So this continued until the edition that I suspect many people are most familiar with, which is the 6th edition, which dates from the middle of 1975. And that's the point where it really, really was everything that you would think of as Unix pretty much all in one place. The hierarchical file system, which was really, I think, in some ways, the central invention, just a way to organize data that is so clean and straightforward and so on. And that's pure Ken Thompson, as far as I can tell. The idea that files contain just bytes. Operating system didn't care what was in the bytes. That was the responsibility of the programs that dealt with them. And this idea that the other things could, in fact, have an interface that made them look like file systems, devices, for example, so that the keyboard or the screen or something like that could be a file as well. It had a programmable shell. It was not very well programmable at that point, but it technically was, I guess you'd say, Turing complete. You could actually write programs in the shell. It had regular expressions, these text patterns that go along with the fact that so much of the system operated fundamentally on text. And pipes came along roughly in 1973, I think. I have the date somewhere, but not right here in my head. And then lots and lots of interesting tools, languages, ways of using computers that in some sense were all more or less original, or at least the way they hung together and worked well and were properly documented was definitely original. And finally, this enormous step that the whole system was written in a high-level language. It was written in the C programming language. That happened for the 3rd edition. And so it's about 9,000 lines of C. Now, actually, that's a slight lie. There's probably 300-400 lines of assembly language, which you need for interfacing with the hardware, getting off the ground, all kinds of things like that. But fundamentally, it was a C program. And that meant a number of things, which we'll talk about in a sense. But one of the most interesting aspects of it, and something that probably helped the propagation of Unix over the years, was this book. Now, this is the commentary on the 6th edition, which was written by John Lyons. John was actually from the University of New South Wales in Australia, but he spent a couple of years, separated years, at Bell Labs. One of them was across the hall from me. And what he did was to take that 9,000 lines of code and write them in one volume of this, and in the other volume explained what they were doing on a line-by-line basis. And it's an amazing way to see how an operating system works. This is not the original format of this. The original format, in fact, I have them in my car, but I decided they were too precious to bring in a crowd like this. So they were numbered copies, and you had to sign for one inside Bell Labs to get a copy. So I still have my numbered copy. This eventually became enough public domain that a publisher made these, and of course you can see all of it online as well. Well worth looking at if you haven't done that already. Okay, so that's the code, if you like. I mentioned pipes as an interesting and important aspect of the operating system at the time. The idea for pipes came from Doug McElroy. And, you know, Doug is sort of an unsung hero in all of this, that he, in fact, contributed an enormous amount, but often behind the scenes. But Doug had this idea, which he expressed in 1964. So this is almost a full decade before pipes appeared for real. This idea that in some sense, it would be nice if you could take programs and think of them as chunks of garden hose and just screw them together as you needed them to do some kind of processing. So the upper half of the slide looks kind of crappy because that is a scan of a piece of paper that hung on my office wall at Bell Labs for 30 years. I don't know where it's gone now, sadly. But that's the idea of pipes. Pipes showed up in the operating system in a very, very short period of time, literally sort of overnight, as Ken Thompson figured out how to put them in the code itself. And you can see them in that version 6 system listing because it's not actually very complicated. But the idea of pipes suddenly changed the way that people thought about programming, I think, because the idea you can connect the output of one program to the input of another, and you can do it in a syntactic form that's just so easy and natural you don't think about it. It's just like you type the command. So who tells you who's logged into the system? You want to know if Joe is logged in, you run that through grep, the pattern searching program, and then count the number of times that Joe's logged in. So that's the kind of thing you would actually do on this small, tightly knit system that we used. So when pipes appeared, and as they say, almost overnight, there was this frenzy of people changing programs so that they would work properly in pipelines. So, for example, they would read not necessarily from a list of files, but also from a standard input, so they could be a sink for information. And they would produce output on a standard output so that they could be a source for a pipeline. And they didn't produce nonsense error messages on the pipeline because those would screw up the processing downstream. And things were packaged that way, even if they don't make logical sense. For example, think about the sort command. Okay, I'm going to sort an enormous amount of stuff like this. I can't produce any output until I've seen all the input, right? But that doesn't mean that you shouldn't put sort in a pipeline as a natural sort of thing to do, so to speak. And so sort just works that way, even though it's cherishing up all the input until it's able to produce any of its output. And things like that made it possible to do this weird thing that Steve Johnson came up with, the pipeline for detecting potential spelling mistakes like this. So you can concatenate a bunch of files, translate them into lowercase in case they're capitalized, then sort them, and that's a full stop in the pipeline while you get them all, and then throw away the duplicates, and then compare them to a dictionary. And if the word is in the input but not in the dictionary, it's a plausible contender for being a spelling mistake. Not perfect, but this is kind of a one-liner, and it tells you whether it's right. The other thing this led to was modularization of programs, so that, for example, I worked on document preparation programs like TROF for a long time. TROF was already up against the stops of the machines of the PDB-11. There was no room for a bigger program. But with pipelines, you could pipeline input, and so we created programs that would be preprocessors for TROF. So EQN handled mathematical notation. Think of it as a precursor for LaTeX. Mike Lesk did this thing called TBL, which did the same thing for tables. I did one for pictures. John Bentley and I made one for graphs, and these things just strung together. And it didn't matter as long as each individual program fit in the memory, but something that combined all of those would first have been a mess, and secondly, wouldn't have fit. Part of what made all this possible was having a programming language that was easy and nice to work with. And this was the work of Dennis Ritchie, building on BCPL, which was done by Martin Richards at Cambridge in England. Martin Richards brought that to MIT, and it was used for a while as an implementation language on Multics. In fact, Ken Thompson, in his usual fashion, found the essence of that and made a smaller language called B, and then Dennis made this language called C. B was typeless because the machines that it was running on had only basically one type, the integer this big, and whereas the PDP-11 had characters and integers and eventually floating point. So this was a very, very effective language, and you could do anything with it, and it was efficient. And it was at a time when efficiency mattered because the machines were actually pretty wimpy. As again, I don't have to tell people here, most machines didn't have very much horsepower. They didn't have much memory. They didn't run very fast. So you needed a language which was a pretty good match for what machines looked like. So anyway, the advent of C led to just an explosion of applications that you would call today system programming, and in particular things like language creation tools like Yak and Lex, and then the things that went with them. And then Steve Johnson had the idea that, gee, you could sort of separate the input side of a compiler. I mean, it's probably not an original idea, but separate the input part of a compiler, the parsing and figuring out what the statements are, from the code generation part, and then you could have code generation for different kinds of machines, and there were a lot of them in those days. So Steve Johnson's portable C compiler led to the portability of lots of programs that ran on Unix, and then eventually to the operating system itself. And so there were a lot of these things. There was an Interdata port that Steve and Dennis Ritchie did, and fax, so on. What happened is that the availability of a portable operating system and a portable language and a collection of really, really useful, interesting tools altogether made it possible for somebody who had an interesting idea to go and form a company that would build a computer, and all the software was basically available. And so that's the genesis of the workstation market, things like Sun Microsystems and MIPS or SGI and things like that. They were all based on the idea that here's this essentially free software that's a complete set. All you need to do is figure out the compiler that makes it run on your hardware. And so this bizarre slide is something that I think most people don't realize, that at one point, Microsoft was the largest distributor of Unix systems. And you sort of wonder how the world might have evolved if Microsoft had been just marginally smarter at the time. But who knows? Anyway, it didn't happen, and they went off in their own direction. Anyway, so anyway, what else? One of the things I've sort of hinted at this, Unix was very, very good at tools of all sorts, and some of these were implemented as domain-specific languages. That's kind of been my thing off and on for years. Many of them were these small tools. I've mentioned grep, pattern searching, diff, comparing two files. Everybody knows all of these things. Of course, sort, we talked about just counting things, and a programmable shell. So the 6th edition shell was not terribly programmable. The 7th edition shell, which was done by Steve Bourne, was very much more programmable, though in a sort of odd syntax, I guess we could say. And then these tools for making languages and so on. And this image of the building blocks came from that. This is some PR photograph, which I thought was actually fairly well done at the time. And you can't quite see it, but behind that is text. It's actually TROF commands for some document. I have no idea what it is, but I provided it, so I figure it's fair game for me to use it. Anyway, everybody here knows grep, and I think when Ken was here with me 6 years ago, he talked briefly about the evolution of grep, and I thought I would at least mention parts of it again. Basically what he did, grep, everybody knows this, right? Grep is a program that just searches through arbitrary input, either standard input or a set of files, for a pattern expressed as a regular expression. And it's kind of the quintessential small tool in Unix. Ken created it by doing surgery on the Unix text editor ED, which is, of course, passed mostly into disuse at this point. But anyway, I got a call from somebody I could probably date it fairly accurately. Audience survey, when did the HP 35 appear? 1971. So the story dates from 1971. Thank you. I got a call from this guy in 1971 who said, I've got an HP 35 pocket calculator, and I noticed that when you hold it upside down, some of the numbers make letters. And he said to me, I never forget it, he said, what works can I make on my calculator if I hold it upside down? Well, as I said, I was in a research operation. Murray Hill was research, and so it was very nice to be working on the frontiers and helping people with real problems. So I said, okay, what letters can you make on your calculator when you hold it upside down? And he said, BEHILOS. Burned into my brain. This is not very good, but you can sort of get the idea. And I said, okay. And you can guess what I did. I stepped to the keyboard and I typed this command. Okay? And everybody here, I'm sure, knows that this is simply look for all the lines that contain arbitrary number of any combinations of those characters and nothing else. Okay? And the input is the word list from Webster's Second International Dictionary. So it's just the words, one word per line. Okay, so it's sucking out the lines that contain exactly things that he could make on his calculator if he holds it upside down. Okay, Webster's Second International, which dates from the 30s or something, is a very big dictionary. It had 235,000 words. And so I pushed return, and out came an astonishing list of words. There's sort of 250-ish, I've forgotten exactly. Now, I'm a pretty well-educated native speaker of English, and there's a bunch of words there that I don't know what the heck they are. So anyway, I printed this and sent it off to the guy, and I guess he must have been happy. I never heard from him. So anyway, this, I think, in some sense, this period of the 70s and I will say the 80s was kind of the golden age, if you like. So Unix was everywhere, was on everything, all the computers that people had. C and its descendants were everywhere and on everything. The tools, the languages, and so on were widely available. And people started to get recognition. And the most obvious one is that in 1983, Ken and Dennis won the Turing Award for their work on Unix and C. And there was even public awareness and recognition that was outside the technical community. To pick one random example, this is the National Medal of Technology in 1998 with a politician you will remember. And perhaps better known, popular culture thing. Yes, I figured this is, if there was ever an audience which would know what's coming next, this would be. Yeah. Like Smurfy, she was, I've forgotten what her name is, Ariana Richards, I think. Anyway, so this was the peak, if you like, in some sense. And I think what happened in the late 80s, early 90s is that a lot of things started to take a toll on this up to that point, very successful sort of thing. There were certainly commercial pressures because Unix was become a commercial force. There were divergent versions. There was that big split between BSD and AT&T versions of Unix, which was a real nuisance and involved a lot of pointless lawsuits and things like that. Lots and lots and lots of people started making contributions to Unix, and with due respect to all of us, they most of them were not of the same caliber as Ken Thompson and Dennis Ritchie, so they were not necessarily good. Also, hardware continued to get cheaper, right? We're riding a Moore's Law curve quite strongly, and so that meant there were fewer constraints. Processors were faster, and there was lots and lots and lots of memory, so you could be much more careless in design and the way you wrote programs, which led often to what I would call bloated software. And then the other thing that happened is that Microsoft produced the PC. IBM produced the PC. Microsoft produced the software that went on it. Let me say that right. And so a lot of effort, focus, and talented people started to work in the PC world, which was different in a lot of ways. Then so the good ideas and the talented people sort of drifted away to some extent, or even a lot, from Unix. And for example, there was much more of a focus on interaction because in part, Microsoft Windows or Microsoft DOS were consumer products. They weren't meant for a technical population, so it was different goals. So that was kind of a downer in some ways, but at the same time, things started to happen that were up again, and in 1991, you have the evolution, or the initial development of Linux, which becomes, in effect, the Unix system of today for an awful lot of people, and that keeps this legacy of Unix alive. So what is the legacy? I would say that these are the kinds of things that are contributions of real import from what went on there. The hierarchical file system I mentioned before, I mean, that's the way you build a file system. I mean, Google Drive notwithstanding, that's the way you build a file system. The use of high-level language is now standard for writing software. I mean, that's just what you do, except in the most extreme situations. The programmable shell, a very, very useful thing. Pipes, obviously, and these programmable tools. The use of text as the interchange medium was, in fact, very, very effective, and regular expressions went along with that. And then something that's maybe not as much recognized, but we do it all the time, which is programs write programs. Okay, and you know, compiler creates assembly language or whatever. That's a program writing a program. All that collection of preprocessors that I mentioned, those are programs writing programs. And once you get it right, programs that write programs do a good job. They do it often better than people do, although you have to get it right. I will pass over what's happening with large language models in this, because my few attempts on that have kind of invalidated what I just said, but okay. But I think, and perhaps the most important thing was that there was a philosophy of how to write software that I think had a lot going for it, very, very useful way of thinking about it. So Unix is, at this point, call it 55 years old, something like that. And this quote from Doug has always appealed to me, that Unix is an improvement on its successors. And you could argue that that might be true in some respect. But certainly most of what made it as useful as it was in place by that 6th edition in 1975. There are obviously very, very important things that have happened since then. Networking is perhaps the most obvious one because computers just now talk to each other all the time. Graphical interfaces, which are much more friendly for people who are not technical in many ways. And then, of course, computer architectures exploded in all kinds of ways. Multiprocessors, multiple cores, you got the threading, GPUs, you name it. Something else that's different that would have been hard to retrofit but is now very important is the use of Unicode, so that rather than having an infinite number of different character sets, we have basically one character set, and you could sort of count on software working with it. It's all. So I think those are the things that are in Unix and then the things that have come along since. So how did it actually happen? It certainly wasn't planned. And it certainly wasn't driven from top down. It was driven from the bottom. And I think sort of what I see is two really, really first-rate people, just uniquely qualified, with very good taste, and then a pretty reasonable supporting cast. So it was part of that supporting cast, in particular, Doug McElroy, was management. So you have to have some kind of management. And the management at Bell Labs, I think, on average, was very good, enlightened, and left people alone if it looked like they were doing anything that might be remotely useful in some sense. I mentioned hardware is cheaper, and so that made it possible to do things. I think if Unix had come along on PDP-10, it would not have been successful, but on a machine that was a tenth the price, it could be. And of course, the Bell Labs working environment, this is probably rosy glasses at this point, but I think it was very good. Certainly the funding was stable. It was not, what have you done for us this quarter, but whether it's, have you done anything in the last 3 or 4 years? Slightly overstated, but not much. A very stable organization, a very flat management structure, which is something I didn't put in here, and this long-term view because they had a goal which is fundamentally to do universal service. That was the AT&T motto, universal service. And then just as a working environment, it was great fun to hang out with these people. It was cooperative, it was collegial, it was not competitive. And so all of that was very good. So could something like this happen again? I think it depends very much on your, on maybe what the target is, but there are things that work in your favor, right? There's no shortage of good people. There's always good people, and there's often good management too, if you think about it. Hardware is cheap, software is free, internet's everywhere. So there's all these things that you need to make something that will use a computer to do some work. They're all there. It's hard to find the environment that makes all of that happen all at once. However, I think industrial research tends to be off to the side, and perhaps more important, it's short-termish. It is more, what have you done for us this quarter, than why don't you think about something important for a few years. And academic research is strapped for money very often, and that's a problem. But, it could happen. If you think about the number of things that have been the result of just 1 or 2 people with a good idea and then carrying it off. Linux is a nice example of something one person with a good idea and carrying it off. Most of the programming languages that we use are 1 person, basically, or 2, or conceivably 3, but no more than that typically. And certainly some of the companies that we deal with started with a couple of people who had a good idea, like Microsoft or Apple or Google or Amazon. And so there's lots of those kinds of things. So I want to finish with one observation from Dennis Ritchie, which I think is actually kind of important, relevant in a way. This comes from the paper that he wrote called The Evolution of the UNIX time-sharing system in 1984. And he said, basically, what we want is a system around which a fellowship could form, that people could work together, that it would encourage close communication. And I think that's very important. If you look around here, that's what we're doing, right? This is a fellowship of people, weird people, all of us, who are interested in how computing has evolved over the years and with an eye to picking up what was the good stuff in the past and then coming together at a time like this to communicate it. So I think this is, in some sense, the essence of the UNIX experience and many others as well. So anyway, that is all I wanted to say. I thank you very much for your attention. It's been fun to be here.
If you have questions, please wait for a microphone.
So you teach now?
The question, do I teach now? Yeah, not right this instant, but start. Yeah, no, I'm still teaching at Princeton. I have not yet retired, and woo! Somebody else? Get the microphone.
Hi. I have kind of one question that's split into 2. My first question is, well, I guess my overarching question is about Plan 9. My first question is, do you think that Plan 9 offered some technical benefit over Unix? And my second question that's kind of a follow-up is, why do you think it didn't really succeed? Should it have? Yeah.
Yeah. So Plan 9 was, in fact, done at Bell Labs research, that same group of people with many of the same cast of characters. Ken Thompson and Rob Pike were very much involved. Rob Pike was probably the most active of it. Plan 9 was an attempt to remedy the defects, the flaws, the imperfections of Unix and to make it better for a networked kind of environment. And so it put together a bunch of interesting ideas. It took, for example, keep doing that. The idea that devices are files in Unix, Plan 9 carried that to an extreme degree. Almost everything was a file system. So for example, your shell environment was a file system and the variables were files. So it carried that to a considerable degree. And I think that was an interesting set of ideas. It had some really, really nice ideas for windowing. The problem with it, and I speak as somebody who was there but didn't use it, the problem with it was, in some sense, the embedded base. It did not cooperate easily with existing Unix stuff, and the Plan 9 operation took a sort of Procrustean view. You will do it this way because that's probably the best way to do it. And that meant that programs that somebody had already written for conventional Unix, like using the standard I/O library, would not work on Plan 9 unless you did a lot of work to convert them. And conversely, Plan 9 programs would have to be, damn it, converted. One of these days I'll just break it. Plan 9 programs had to be converted to work on Unix, and I think that barrier between the two systems was a major impediment for a lot of people. It certainly was one of the reasons why I did not do very much with Plan 9, in spite of its manifold really good ideas. So,
what was the impact of open source on Bell Labs, and how did Bell Labs look at open source I was having, and like, you know, were there like pictures of Stallman with like wanted signs on him? Like, do you have any thoughts on any of that?
My expertise with the open source stuff, I would say a lot of what happened at Bell Labs was, the part that I knew about best was in a way over before the open source movement got really rolling. I think of Stallman as being the mid-'80s or something like that. What Bell Labs did was inadvertently create something that was not meant to be open source, but which turned out to be open source. What they did was to take that source code in particular, the 6th edition code, and license it to universities for educational purposes at a nuisance fee, basically the price of making a magnetic tape. And so what that meant was a generation of students and their faculty grew up using Unix and exchanging software back and forth and around and so on. The slide that I showed with the sort of kids surreptitiously Xeroxing that stuff, that was because that source code was supposedly proprietary, but people ignored the proprietary aspect after a while, and so it was de facto open source, although not certainly legally. I don't know that Bell Labs ever, and AT&T, the part of AT&T that sold software, I don't think they ever really got the idea of open source, at least as I remember it. So it's kind of an evasive answer, but I don't think that it was really part of their worldview at all.
I have an observation rather than a question. I worked in the development side of Bell Labs using Unix to write software and systems to support AT&T's operations. The one thing that another part of Unix portability is that we were portable. We could move from organization to organization, system to system, and not miss a beat. We could even leave Bell Labs in New Jersey, settle in California at Sun Microsystems, which a lot of us did, and not miss a beat. So Unix was portable software. It was also portable programmers.
Yeah. I think that's an actually very interesting observation, that because so many people learned it, used it, students learned it in school and then wanted it when they got into real jobs, all of that thing did in fact make a cohort of people who had that common base of expertise and knew how to use it no matter where they were or where they were working. You also touched on something else that's quite intriguing, which is the use of Unix inside Bell Labs for basically operational support systems, of which there were many, because the telephone company had just a huge number of things to keep track of in equipment and circuits and just all kinds of stuff. And a lot of that became essentially Unix systems over the years. Yeah, so thank you.
So as someone who's unfortunately was a little young to use a teletype in anger, I have a question about like a kind of a how it was question, which is specifically, first of all, the famous picture of Ken and Dennis, they're at Teletype Model 33s, which are ASCII 63, so they're capital only. They don't have they're missing some characters. And early Unix doesn't have those characters. And my question is, by the time C came along, were you all done with those teletypes? Or if not, why is it the case that C uses characters that aren't on those teletypes? Was it, like, do you have some intuition as to how we came to that place?
Yeah, I think the answer is that the Model 33 came along first because they were made by AT&T, and so they were available. But as you point out quite correctly, they were essentially uppercase devices only with at most 64 characters. But very soon after that, and I don't remember the exact date, came along the Model 37 teletype, which had upper and lower case. And so most of the software after that first 2 or 3 versions of Unix was using still paper, but the Model 37 teletype, which was almost as much of an upper body developing device. You really had to push on it, but it had a full character set, and so that was the important thing. It also had some, this is a story which I don't know I've ever told before, it's certainly not here. It also had some weird properties because it was tractor feed paper, so it was fan folded but with holes along the sides so that it could be pulled through and maintain alignment very easily. But one of the things you could do was you could run it backwards. That is, you could take the paper out as well as in. And I still remember Robert Morris Sr. sending an email to Joe Osana, which contained 100 reverse line feeds. So it sucked the paper out of the 37 and dropped it on the floor. And you don't want to have to thread the paper on those things. Thank you.
So, as someone who has effectively been, involved in software for the life of software as a commercial thing, and being that you're in a place where I think everybody in this room is going to say, "Oh, things used to be so much better." With the massive changes and the commercialization and productization of software and computing, do you have any hot takes on the current state of software as it exists today and is used today?
Okay.
Big 10 words or less, if you can.
A lot of it sucks. I could elaborate, but maybe offline. Unfortunately, it's all too true. I'll let somebody else ask a question. I'll grab you after.
Brian, thank you so much for being here and sharing everything with us. I have a question about early Unix and data access, such as database files, ISAM, and where that came into play for starting to build applications and systems that could really access and store data.
I don't think that data in that sense was ever a part of the worldview of Ken and Dennis in particular. At the time that Unix was being done, the dominant commercial system was probably IBM's System 360, which had a bizarre notion of file systems where every single property of a device showed up in its what you had to do to make it do anything. And so it was very complicated to just access information on files, on devices in the IBM file system. And the idea of actual honest-to-God database, which would be organized in some way, I think was not part of it. There were occasional, not even that, I think most things were simply, here we got text files, and if we need more structure, we could put it on, but it's not a database system. One of the strongest evidences for the fact that there isn't such a thing, you've all seen, maybe never used, the DD command. The DD command is a... It is actually derived from some part of the mysterious job control language that you had to say to an IBM system to make it do something. It was, DD equals. That's JCL. Yeah, that's where it came from. So I think that the already too long answer to your question is no.
There was, so ISAM or any kind of data model like that?
No, not at all.
Not at all.
Brian, first, thank you for sharing all this information with us, and I think we all feel very good about it. A question, did any part of Unix end up in the switching system of Bell Telephone?
I do not know that it did. There was certainly an influence somewhere in, make up a number, the early to mid-'80s, something like that. It's probably earlier than that. Somebody who worked at Indian Hill in particular could check me on this. But they started to write the software for the big switching systems, the number 4 ESS and number 5, where it's written in C. So at least that was being used. I don't think that any software that came from Unix itself found its way in, but that code was fairly, seriously proprietary, and so you didn't get to see it. I mean, at one point I got a chunk of number 4 ESS code, but it was not something that was given to very many people. There was another thread of development, probably a little later, that AT&T made a PBXs, private branch exchanges, phone systems for a company inside the company called Dimension, and they made those in Boulder, and we got involved, not me personally, but a number of people got involved in looking at the software for the Dimension PBXs, and we even had a Dimension PBX that we got, and it sat in Murray Hill, and people like Ken wrote code for it, so we had our own version of an internal telephone switching system called TPC, the phone company. And that was an experiment in what's involved in actually doing telephony, but I don't think that ever went anywhere.
Hello.
I can keep going as long as people don't mind, so pass the mic around. There's
Hello. Given that so much of the history of Unix centers on academics, scientific institutions, and I guess intelligentsia, I'm wondering, how do you feel about Unix kind of filtering into the layman community vis-a-vis more recent versions of Mac OS being Unix-based? So OS 10, iOS, basically anyone who has a Mac or an iPhone or an iPad is using Unix and they don't even know it. I'm just wondering, how do you feel about it kind of deviating so far from the original free open source philosophy?
I think you hit the nail on the head when you said that most people don't know it. Yeah, and that I think is absolutely true. If you ask the average person who has an iPhone, which is a reasonable fraction of everybody here. Well, sorry, this is the wrong audience. Most people don't know that, in fact, their iPhone is running at this point, fairly long path of evolution version of Unix, and of course Android phones, which make up the other fraction of it, are running a different flavor. They're Linux underneath all of that. So most people don't know that. I think from my side, as just somebody who was involved loosely in the early days and has a phone, I find it intriguing, and I also find it kind of irritating that underneath there is a system that I could do things with, but I can't get at it.
So obviously the computing world has changed a lot since you first started out, but do you have any advice for someone in a younger generation who's very interested in computers and, is kind of making their way through the world?
it's hard to avoid cliches on this, so I will apologize in advance for anything that sounds like cliche. But I get asked analogous questions by some of my students, for example, and many of those are, in fact, computer science students. What should they be doing? Where's the action going to be, et cetera? And the answer, the real answer is I don't know. I think probably computers in useful forms where you could be doing things with them will be with us for a very, very long time. It may be that most people will not really realize the extent to which what they do is controlled by software that runs on hardware that uses a communication system. But you, if you do this stuff, will know that, and I think that will give you something to do that will be interesting and probably actually employable for some time in the future. The other thing, and this is the real cliche, is if this stuff turns you on, do it. Okay, if it's really interesting, and obviously you could see all around you people who are turned on by this kind of thing in various odd and strange but fun ways. Not to name any names, but I think you can do that kind of stuff, and you can have a good time, and you could probably make a living and enjoy what you're doing. So that my advice would, the cliche is follow your passion. That's incredibly badly overused, but I think doing stuff that you find intriguing is the way to go.
Hi. Can you say a little bit about the pipes and the standard file handles, standard in, standard out? Were those ways to implement pipes, or did they have a earlier sort of beginning?
Yeah, the standard input and standard output was there essentially from day one. That every program had an input stream, which was just file descriptor 0, if I remember correctly, and an output stream, file descriptor 1, and they were part of every program. So every program could read the standard input, write the standard output. Now, what was the standard input and output? Well, by default, it was the keyboard and the print mechanism that went with it. But the shell, right from essentially the beginning, had this redirection mechanism so that you could say less than a file name, and that the shell did the connection to connect that file as the source of input instead of the keyboard, and similarly the greater than file did the connection to an output file. So all of that mechanism was there essentially from the first edition, and the pipe mechanism was simply saying, oh, we could do yet another kind of connection with that. We could take the output from the program, and instead of sending it to a file, which is all sitting there in buffers in the I/O system, we could send it to another program. And then you need the pipe mechanism is how do you connect the file descriptors? That's pretty easy. And the other is synchronization so that when somebody's writing a lot, it blocks if the reader isn't reading enough. But other than that, it's really not very much code. If you look at that 6th edition code, yeah, it fits probably in, 30, 40 lines or something like that. It's very, very short. So.
Thanks for the talk. It was really nice learning about UNIX. So I'm sure you might have a lot of insight. You might have a different perspective on this, but I'm sure you've heard of Rust. This popular systems programming language, and a lot. Well, yeah, and like everyone says, oh, Rust will replace C. What are your opinions on this? Do you think there's any sort of merit to C replacing or Rust replacing C, or is this just a huge hype bubble that's waiting to die down?
Oh, Rust.
Yay!
Okay. I have written only one Rust program, so you should take all of this with a giant grain of salt. And I found it a pain that I just couldn't grok the mechanisms that were required to do memory safety in a program where memory wasn't even an issue. But I think I could have gotten around that. The other thing that I found was that two things, really. One, the support mechanism that went with it, this notion of crates and barrels and things like that, was just incomprehensibly big and slow. The compiler was slow. The code that came out was slow. And the other thing is that when I tried to figure out what was going on, the language had changed since the last time somebody it posted a description. And so it took days to write a program which in other languages would take maybe 5 minutes. And so that was my one Rust example. I actually got mail from a friend a few days ago. A project is being started somewhere called Tractor, which is, somebody's heard of Tractor. I had not heard of it. It is total replacement of all C programs with Rust or something like that. It's a tortured acronym that goes under it. So I'm probably unduly cynical, but I don't think it's going to replace C right away anyway.
Thank you. Brian? Over here.
Way back there.
Thank you. I can't see again.
First of all, I would like to thank you personally for all your many amazing contributions. And I'm sure many people here feel that we owe our livelihoods, in a sense, to a lot of the work that was done by you and others at Bell Lab. So the question I have is about a book that you wrote in the early 80s called The UNIX Programming Environment with Rob Pike. I would say it's one of my favorite books on programming or software in general, because it seems that it presents a coherent view about problem solving, just in general, but particularly on Unix, and that it's so concise. It's really amazing. And I wonder if maybe you could give a little background on how that book came to be, and do you think a book like that could be written today?
So the book came about just because Rob and I were literally in the same corridor at Bell Labs, and we had talked about possibility of writing a book about something, and we were using Unix. This was very early 80s, I guess. The book came out in 84, if I remember. So we talked about it. We had ideas about what might go into that. How would you explain what the system was, how you wrote code for it, how you took best advantage of the features that it had. And so it came together, I think, reasonably clearly because of that. And I'm certainly very happy with it. Rob was an absolutely fantastic person to work with because not only is he just a super good programmer, but he's also an extremely good writer. And so the combination was very much to my liking. The question is, if you wanted to update that book today, and Rob and I have talked about this from time to time, I think it would be too hard because we hit it at about the time when there was sort of the cleanest, simplest stuff. Networking had not appeared. Graphical interfaces had not really appeared. There was really only kind of one core Unix-y system around. And so life was a lot simpler. And I think at this point, too many things have grown up to make it possible to write an updated version of that. We talk about it sporadically, but I suspect it will never happen, sadly.
Hello. Thank you for giving this talk. I have a probably over-asked question. What's your favorite distro?
What's that word? Yeah, as you can see, I'm using a Mac here, although in many respects I'm using it mostly as a term, not here, but when I'm in my office or home, I use it as a bunch of terminal windows to whatever Linux system the computer science department is running at any given moment. And I don't even know what it is. So sorry, I can't be more helpful than that. So maybe a couple more, and then we should probably let people get out of here. Who's got the mic?
Thank you so much for your lovely talk. Given your very pioneering role with C, are you familiar with the language, the derivative Holy C? Do you have any thoughts on that?
Okay, so the short answer is no. The slightly more extended answer is, does this show up on websites like 99 bottles of beer on the wall? Okay.
This last two questions?
Yeah, sure.
Okay.
What was normal for file access before the hierarchical file system?
There were some of them. It was not very organized. I mean, these comments about the IBM 360 file system, where it wasn't I mean, they stored information on disk, but it wasn't really organized in a form that a programmer could easily understand what it was. CTSS had a file system, but it wasn't hierarchical, so it was basically one level. There was directory and then files within it, and that was essentially it. So the hierarchical nature is you could, have directories inside directories inside directories, and so you could go further that way and then be very systematic about it. Trying to think what the Multics version of a file system was. They were trying to map the file system into virtual memory segments, and so it was a completely different take on things. And I think maybe that was a good idea, but they couldn't make it work well enough at the time, at least as I remember it. Now, memory is dim, and I didn't work on Multics per se, so that's a partial answer.
This is the last question.
Who's got the mic?
It's me, over here. Hi, Brian. What are your thoughts on Nix and Nix OS?
God, it's another one I've never heard of. Yeah, no, I think I've heard it, but I don't know anything about it, so I can't give you an answer. I apologize.
Thank you.
Okay, everybody give it up for Brian Kernighan.